All right, let's talk about something we all know, but maybe don't really know. Gravity. I mean, we feel it every single second, right? It's what keeps your feet planted firmly on the ground, and it's what keeps the entire solar system from flying apart. But what is it actually? It's funny, it's one of those things that's so familiar, but at the same time, it's incredibly mysterious.
Okay, so to kick things off, I've got a question for you, and it might sound a little weird. Just look at your phone for a second. Go ahead. Are you and that phone attracting each other? Like right now?
Believe it or not, the answer is yes, absolutely. You are literally pulling on your phone, and your phone is pulling right back on you. And no, this isn't some kind of metaphor or philosophical thought experiment. It's a real, fundamental law of physics.
So this is the genius idea that Sir Isaac Newton figured out centuries ago. He realized that this little pull isn't just happening between you and your phone. It's happening between every single thing in the universe that has mass. I'm serious. Your desk is pulling on your chair. The moon is pulling on the Earth. Even stars billions of miles away are all gently tugging on each other in this huge, silent, well, cosmic dance.
And Newton, being Newton, didn't just stop at the idea. He basically wrote the rulebook for it. It's officially called the Universal Law of Gravitation. And it's this incredibly elegant idea that explains all those interactions we were just talking about. And you know what the best part is? This grand cosmic rule boils down to a surprisingly simple formula.
All right, so let's pop the hood and take a look at this rulebook. Because if we can understand it, we can figure out the big mystery. Why you can feel the massive pull of the entire planet Earth, but you're not, slowly sliding across the floor towards your bookshelf.
Okay, here we go. The formula has 3 key ingredients. First up, the masses. Pretty straightforward. The more stuff an object has, the more gravity it's got. Easy. Second, you've got the distance between the objects. Now, this one's a little trickier, and it has a huge effect. And finally, there's this little letter G in there. This is kind of the secret sauce of the recipe, a special number that sets the scale for how strong gravity is everywhere in the universe.
So, about that distance part, there's a really handy little trick to remember how it works. Just remember this phrase: invert and square. Sounds a bit mathy, I know, but stick with me. Let me show you what it actually means.
This is where things get really interesting. Distance has this outsized, incredible power over gravity. So if you double the distance between two things, the force doesn't just get cut in half. No way. It drops to just 1/4 of what it was. But if you bring them twice as close, the force gets 4 times stronger. That's the inverse square law in action, and it's totally key to understanding how gravity behaves.
Okay, so that brings us right back to where we started, doesn't it? You and your phone. You both have mass, you're super close. So according to the rules we just went over, shouldn't you feel something? Why aren't you and your phone slowly drifting towards each other right now?
And here is the answer. It's that secret ingredient G, the universal gravitational constant. Just look at that number. It is ridiculously, unbelievably tiny. All those zeros. That's the whole reason gravity feels so weak. That little number dials the force way down. So unless one of the objects in the equation is absolutely enormous, we're talking planet-sized mass here, the final force is just, well, it's so small you'd never, ever feel it.
Which, of course, brings us to the one time gravity is anything but unnoticeable. The pull between you and this gigantic ball of rock we're all standing on. That force is so powerful and so constant that we have a special word for it. We call it weight.
Okay, this is super important because people mix these two up all the time. Mass versus weight. Let's get this straight. Your mass is just the amount of stuff you're made of. It never changes. It's the same on Earth, the moon, Jupiter, wherever. But your weight, that's different. Your weight is the force of gravity pulling on your mass. And since the force of gravity is different on other planets, your weight changes depending on where you are.
And this is a perfect way to see the difference. So let's say you have a mass of 60 kilograms. That's the stuff you're made of. Here on Earth, the force of gravity pulls on that mass to give you a weight of about 588 newtons. That's just the sciencey unit for force. Now, take a trip to the moon. Your mass is still 60 kilograms, because you're still you. But the moon has way less gravity, so your weight would drop all the way down to 98 newtons. That's only about 1/6 of what you weigh here. All right, so we've got weight down. It's the force of Earth's gravity. So let's talk about what that force does. Its most famous trick, of course, is making things fall. But the way it does this, well, it's kind of weird and definitely not what you'd expect.
Okay, here's the classic brain teaser. Picture this. You're standing in a special chamber, and we've sucked all the air out. It's a total vacuum. In one hand, you've got a heavy bowling ball.
In the other, a light, fluffy feather. You hold them at the same height and you let go. At the exact same time. Which one hits the ground first? What's your gut tell you?
Everything in your experience, everything you've ever seen, tells you the bowling ball slams into the ground first, right? And yeah, in our normal world, it does. But that's a trick. It's not gravity's fault, it's air resistance. The air pushes up on the feather and slows it down. But in our vacuum chamber, with no air, it's a perfect tie. They hit the ground at the exact same instant. Mind-blowing, right?
So this special situation, where gravity is the only thing doing the pulling, has a name, free fall. And this is the crazy takeaway. When you're in a true free fall, mass just doesn't matter at all. A bowling ball, a feather, a piano, they all accelerate downwards at the exact same rate. They fall with the exact same style.
Okay, so we've seen how gravity works with small stuff like phones and big stuff like planets. But now, let's zoom out. I mean, way out. Because it turns out, this one simple rule is the master conductor of the entire cosmic orchestra. Just think about this for a second. The exact same force that pulls an apple to the ground is what holds the moon in a perfect orbit around the Earth. It's what keeps all the planets swinging around the sun in a predictable, beautiful dance. That same force reaches all the way from the moon to tug on our oceans and create the tides. And if you zoom out even further, it's the invisible glue that holds entire galaxies with hundreds of billions of stars together. It's just unbelievable. All of that from one simple rule.
And so we're left with this amazing paradox. Out of the 4 fundamental forces in nature, gravity is, by a long shot, the weakest. I mean, you can beat the entire planet's gravitational pull just by jumping. But because it's always on, because it's everywhere, and because it never ever stops pulling, it ends up being the most powerful architect in the universe. It really makes you think, doesn't it, about how a weak but constant force can, over billions of years, build everything. The whole story, from that tiny, secret pull between you and your phone, all the way up to the grand design of the cosmos itself.